Imagine a pre-trained AI model as an apprentice who has spent millions of dollars in compute time reading every book in existence. It absorbs the world's general knowledge, but it has zero practical experience. This pre-training phase forces the model to learn grammar, reasoning patterns, and broad facts simply by guessing the next word across billions of sentences. Yet, if you ask this well-read apprentice to debug a proprietary software stack or draft a highly technical legal contract, it struggles. It knows the concepts, but it hasn't mastered the specific craft. To bridge that gap, you might try prompting. This is the equivalent of handing the model a temporary cheat sheet of instructions to follow for a single task. You could also use Retrieval Augmented Generation, or RAG, which acts like giving the model an open reference book so it can look up specific facts on the fly. But sometimes a task requires a permanent shift in the model's tone, style, or deep logic. When temporary cheat sheets and open reference books are insufficient, you need fine-tuning, the equivalent of rigorous, coached practice. Achieving specialized expertise requires a structural adaptation of the AI's internal behavior, rather than just providing it with better external instructions. The first rule of this fine-tuning pipeline is that you never build from scratch. You select a pre-existing foundation model and begin there. Next, you curate a small set of high-quality, task-specific examples. If you want the model to understand medical jargon or handle customer support, you feed it accurate, human-reviewed pairs of inputs and desired outputs to show it exactly what correct looks like. This data divides into a massive training set, a smaller validation set, and an isolated test set. During training, the model predicts answers against ideal templates. The validation set acts as a filter to tune settings. A feedback loop calculates error, nudging numeric weights to improve. Repeating this continuous, iterative loop forces the model's instincts to align with a highly specialized craft. Doing this across an entire system is called full fine-tuning. It requires updating every single parameter in a multi-billion parameter brain, which demands massive amounts of memory, hardware, and budget. To solve that hardware bottleneck, engineers use parameter-efficient fine-tuning, or PEFT, and methods like LoRA. PEFT completely freezes the base model. It only processes updates on that small, newly added set of numbers, saving immense computational power. These techniques are highly effective for instruction tuning, where a model is permanently adapted to follow direct prompts and behave like a conversational chatbot. Engineers now possess the surgical tools required to sculpt massive AI architectures using only a fraction of the resources formerly required. Once training is finished, the model enters the final evaluation phase. It must pass an unseen exam using that isolated test block of data to prove it is ready for deployment. This test often exposes a hidden danger. Fine-tuning rewires behavior, not facts. It teaches a model to sound like a confident expert, but that does not guarantee the actual truth of its output. This chart visualizes the risk of overfitting, which occurs when a model perfectly memorizes training data but fails catastrophically when encountering new variables. The inverse risk, catastrophic forgetting, happens when learning a new specialized skill completely overwrites the model's underlying general knowledge. The very act of fine-tuning inherently destabilizes an AI, creating a highly capable but brittle system that requires intense human oversight. A deployed model immediately faces external threats. Weak evaluation rubrics, biased training data, privacy leakage risks, intellectual property violations, and malicious abuse can easily compromise the system. Defending against these threats requires active pre-deployment security. Organizations must implement strict data provenance tracking, aggressive red teaming for vulnerabilities, and continuous expert review. Once live, the necessities shift to post-deployment operations. Teams must maintain active monitoring in the wild, enforce hard limits on system autonomy, and retain instant rollback capabilities. A specialized AI's power is entirely dependent on and limited by the strength of its human leash. Ultimately, fine-tuning can specialize a model, but people remain fully accountable for its data, tests, boundaries, and consequences.